Hi, I'm Cynthia Ryder, and I'm thrilled to be with you today as part of the Intoxicating Science Talks, and to tell you about the lessons I've learned from chipping away at the unsolvable riddle of mixtures toxicity. So back when I started graduate school in the early 2000s, in the lab of the incomparable Dr. Jerry LeBlanc at North Carolina State University, he gave me two projects to choose from, both involving this gorgeous crustacean, Daphnia magna. The first project that Jerry gave me to consider was about understanding the molecular signaling pathway that led from exposure to some environmental chemicals to this animal switching reproductive strategies. So normally, the Daphnia magna, an absolute feminist icon, reproduces asexually, so she makes clones of herself, and when environmental conditions deteriorate, she switches strategies, produces some males, and then can reproduce sexually and form resting eggs, which can withstand literally decades of harsh environmental conditions. And when the environment improves, those eggs can hatch and she can go on about her business. So the second very different project that Jerry gave me to consider was about building and evaluating models of mixture toxicity. So without hesitation, I chose the Mixtures project. This choice, which was made intuitively without a lot of self-reflection, has determined my path and my career in mixtures toxicology. And after various career development seminars and taking the Myers-Briggs various times, I've learned that it's perfectly in line with my personal scientific ethos, which brings me to my first lesson, which is it's okay to be a scientist who hates details. So I think a lot of people are drawn to science because of the order of the process. They have enthusiasm for elucidating one step in a long process that leads to adverse reactions. But not all of us can be leaf people. Some of us are forest people. And mixtures is perfect for people like us. It's a big picture topic. It simplifies complex data sets and looks for patterns among the things. So I know that I have to confess to you here today, my favorite part of any talk is the first couple of slides when people talk about why they're studying whatever they're studying, and the last couple of slides when people give you a summary and then talk about the significance of their findings. I have to concentrate really hard on the whole very important middle section. And mixtures toxicology is perfect for people like me. So now I want to tell you a little bit about the challenge of studying mixtures. So I know as toxicology enthusiasts, all of you have been in talks where they start out referencing the 80-something thousand chemicals in commerce. It's a daunting number. It really makes you realize the challenge we face as toxicologists trying to understand the health effects of 80-something thousand chemicals. So now take that 80,000 number and raise it to the power of some other ridiculously large number, and that's the challenge we face with mixtures, which has led some to conclude that it's really not worth the effort, like the author of this paper, who answered the titular question, chemical mixtures, an unsolvable riddle, with, yeah, pretty much. So if you, like me, enjoy insurmountable challenges and thrive in chaos, obviously, then mixtures might be perfect for you as well. So I've talked a little bit about the challenge of studying mixtures, but how do we go about understanding risk associated with exposure to mixtures? We have two choices. We can either zoom in and look at what we know something about, the known knowns, and look at the constituents of a mixture and how they add together. This is called a component-based approach. The alternative is to zoom out and look at the mixture as an entire entity, but treat it kind of like a single chemical. And this is a whole mixture approach. In either case, you have many assumptions you have to make. With the component-based approach, you have to make an assumption that the chemicals you know about are reflective of the entire mixture. You have to assume how the chemicals add together, and you have to assume whether or not they display any kinds of interactions. If you're talking about the alternative approach, the whole mixture approach, you have to make an assumption that the mixture in your test system is similar enough to the mixture that people are exposed to. Which brings me to my next lesson, which is how can you harness criticism to grow your science? So a while ago, I was studying the toxicity and carcinogenicity of a particular whole mixture, a botanical dietary supplement ingredient. So this plant-based product, like many plant-based products, is an extremely complex mixture that has hundreds to thousands of constituents in it. So how did we pick which sample out of all the possible variations to study? Well, we looked at a couple of the marker constituents, and we compared to a reference sample, and we decided, yes, this is representative, and so we tested this in comprehensive toxicity and carcinogenicity studies. So when we went to report these findings, we got some really pointed criticism that the test sample that we studied didn't resemble any other product that's available in the marketplace, and we couldn't say anything beyond the exact mixture that we studied. So what do you do in that scenario? You have many options. The first option is to freak out and obsess over the fact that you wasted $1 million of taxpayer money to study the wrong thing. Your second choice is to deny, just assert that you studied the correct sample. And the third choice is to actually develop a research program to look at how your mixture that you tested in the test system relates to all the other possible variations of that mixture. So choosing this third option has been the most satisfying decision of my scientific career. Not only did that choice lead to a really successful mixtures research project on sufficient similarity of whole mixtures, it also gave us incontrovertible evidence that the sample we tested was similar enough to other high-quality samples that are available in the marketplace. And as an added bonus, we learned that there's a lot of very poor quality stuff out there, which may or may not just be dirt. So that, and many other experiences that I've had, have been where criticism that initially stings is actually a gold mine of ideas and approaches that can be used to strengthen your science. So, 20 years into this love affair with mixtures, I hope that some of the things I've talked about have been useful information for you. But if they haven't, and you've hated everything I've said today, you can come find me later and criticize me, and it will be fuel for my next adventure.